a whole number. And so we're going to say this becomes 5. This is essentially 2. So I have to go 2 times 2 equals 4. So this one, what's 6.77 times 2?
13.54.
I guess that's going to be a problem for us. And then multiply this one times 2 equals 2.
Why did I make that one 5?
2.5 times 2 is 5.
Why can't you just round the 6.77 to 7?
That's what they did. And so here they said that divided by that is 7. I think what the problem is that we rounded that down to 2.1, we rounded that up to 0.31, and in the end it made a difference. If you have something on a quiz or an exam, it's not going to be that finicky, okay? And so in this, what they did is this came out to be 7, and so 7 times 2 is 14. Yours will be more obvious than that. And so now we have 5, 4, 14, and 2. They're all whole numbers. We can write our formula. And so we have Cu5, Si4, O14, H2. So let's. When you do these, number one, look for something that's further away than 0.1. That's going to tell you it needs to be multiplied. Okay? If you're comfortable with decimals, you may not have to go through that process of elimination. What can I multiply this by? Some of it may just scream out at you, telling you you need to multiply by this number. Okay? If you need to multiply by 2, it's going to be something 0.5. You saw that. If you multiply by 3, that means this is going to be something in a third. So 0.33 multiplied by 3. If you multiply by 4, it's going to be 0.25. That's a quarter. 0.25 is a quarter. Multiply a quarter by 4. 0.2 is a fifth. Multiply by 5. 0.1 is a tenth. Multiply by 10. Okay? Most of them will be easy like that. Just don't get rounding happy and start rounding things when they can't be rounded. Okay? I see people do that all the time. So this is our same formulas. This was benzene. This is actually acetylene, which you use for welding. If we think about the mass of each, how many times greater is the mass of benzene than acetylene? 3 times. You don't have to calculate the mass of benzene and acetylene to see that, hopefully. Hopefully you can see that C6H6 is 3 times that. I mean, 6 divided by 2 is 3. This is 3 times bigger than that, and so its mass is going to be 3 times larger. So we can use that fact to now go from an empirical formula to a molecular formula. So when you see a problem like this on a quiz or an exam, it is going to say find the empirical formula in A. In B, it's going to say what is the molecular formula. And so what we're going to do, how we're going to do this, is you're going to have to calculate the empirical formula. Once you have your empirical formula, you will find the molar mass of your empirical formula. You all know how to do that. Once you have that, then you'll divide the experimental molar mass by the empirical molar mass. The experimental molar mass will be given to you. The problem will say you have a compound, It's this percent this element, this percent that element, and the molecular weight or the molar mass is such and such. And so you'll find this so that you can figure this out. You'll calculate the empirical molar mass, divide the experimental by the empirical, and you'll get a number. Let's say the experimental molar mass is twice as big as that. And so that divided by that is 2. That's simply telling you that your molecular formula is twice that. And so you multiply your subscripts by 2. So let's do one of these. Here we have, in this case, we're actually already given our empirical formula, so it's going to save us some time. On a quiz, that's probably not going to be given to you, but because we just did this gigantic mess, we're going to assume and hope that you can do the first part and we'll save ourselves some time. So we're told the empirical formula is CH2. So imagine we did this whole process and we found our empirical formula was CH2. That's really the only part we needed, was the formula at the end. We know that the molar mass is 42.12 grams per mole. What is the molecular formula? So we said we needed to take the experimental and divide it by the empirical. Experimental is what's given to us, 42.12 grams per mole. What is the molar mass of the empirical formula? 14. Carbon is 12, plus 2 from the hydrogens is 14. What is 42.12 divided by 14?
3.
What
It's 3.00213.
3.00213, which is 3. So we know that our molecular formula is 3 times as large as our empirical formula. So we're going to take our empirical formula, CH2, the whole, multiply it by 3, and so 3 times 1 is 3. 3 times 2 is 6. And that's your molecular formula. Let's take our break now. We'll start at 7:30 on that clock. I have your exams. If you want to look at them, you're welcome to look at them. But remember, I need them back. Please don't write anything down, no pictures, no nothing. What did you line?
You do well. I think I'm not. See my area. See, I knew it. I got to take that.
Sir.
Thank you.
a little bit over 100%. That was my mistake. Feel good for you? Feel good?
You want to stay here?
I got scared. Yes. I got scared. Yeah, I don't know why. I'm here for this kid. These are both here. Colton, I didn't get a stamp.
Okay. I didn't end up. Yeah, either one.
I reviewed it and it's still there.
How'd you do on the,
Just do it on.
how'd you do on the, no, we asked.
I expect.
Pretty good. Pretty good.
I just went for like
So you killed it. I got scared here.
You did better.
Yeah.
That's the third down.
These were fear. That was just fear. I saw Hexa for some reason. I
But
thought,
did you do your secrets right here?
no, I got the kitty. If I dropped a 6, I would have been good.
I can't remember to put the ID.
Did you get the kitty?
Got it.
The stick pigs? I got the kitty.
For me, I did it right except this.
Damn. I saw him walking. But I like to know you, brother.
Yeah, it's bold, it's bold, underlined, and italicized.
Yes.
I thought maybe I didn't do one of them.
How do you get those stamps?
My wife got them for me.
Nice.
They're custom made.
Oh, that's the fancy stuff like kitty cat.
They don't sell at Walmart.
I know.
last name, comma, first name.
I don't think so, yeah.
Thank you.
Actually look at
I can do the
That's it down. Thirty.
Okay, thing is, I'm wrong. So what's easier for you?
Yes. Did you already?
I'll probably pick up three.
You're all three good.
That's the end. But, I'll buy it. For, that's an order of looking at the car. Yes.
Does anyone still have their exam?
For real. Focus on something. I got no problem.
Yeah, I don't.
No, I want it.
I've seen them for like.
No, does anyone still have their exam?
Horse depreciate that. It's not working.
Okay. So we're going to pick it back up where we left off. We are still on molecular formulas. So we're going to do another molecular formula problem. And this is like what an exam question would look like. So we're starting from percentages. We need to find the empirical and the molecular formulas. Normally on an exam it will be broken down into parts A and B, but it's the same thing. So all we have are percentages. We're also given the experimental molar mass. Remember, that is for the molecular formula. So we have to find our empirical formula. So I'm going to take my percentages, turn them into grams. Got 28.93 grams potassium. 17 grams sulfur. 27.3 grams oxygen. What is the mass of potassium?
39.1.
So I'll convert them all to moles. Hopefully you're all comfortable with that at this point. What does the potassium come out to be? .74. What about the sulfur?
.74.
4. And the oxygen?
2.96, sorry, 2.96.
2.96. So do I round these to 1, that's 3, and call it good?
No.
No. What do I do?
Divide.
Divide by the smallest one. In this case, it's 0.74. So that's obviously 1. That's 1. This one, I don't know.
It's 4.
What does it actually come out to be in a calculator?
4.
Okay. I guess it would. 4.
You didn't believe him.
I thought he was jumping ahead and rounding on me. So now, what do we do?
You make your molecular formula.
Right, empirical formula.
Oh.
Empirical formula. These are whole numbers, so we don't need to round, we don't need to multiply, we don't need to do any of that. And so we can make our empirical formula straight from this. So we have K1, S1, O4. That is our empirical formula. And so if this was on an exam, that would be your answer for part A. Or if there was only one blank, you would like draw an arrow and say empirical formula or something, letting me know that that is your empirical formula. How are we going to find the molecular formula? I have to find the mass of that, right? And so, what does that come out to be? You've got potassium's a 39, sulfur's 32.
135.2.
135.2 grams per mole. That is the mass of that. 135.2 grams per mole. Now what do I do with that?
270 divided by 135.2.
270 divided by 135.2 equals what?
1.997.
1.997. Now what does that number look like to you? 2. So we're going to say that's a 2. Now what do I do with my 2?
Multiply it by the
Multiply it by the subscript on all of those. K2, S2, O8. If you don't remember which one goes on the top, the big one goes on the top. It is literally impossible for the empirical formula to have a larger mass than the molecular. That cannot happen. And so either the large one goes on top, or if they're both the same number, it doesn't matter which one's on top, right? It's going to come out to be 1. Put the big one on top, divide by the smaller one. Whatever you get, that's your multiplication factor. So that is empirical formula, that's molecular formula. The only thing I can do on an exam to make that problem harder is maybe make you do a multiplication at this step. That's all I can do. Once you have your empirical formula, that is the work. I cannot make this more difficult. I can make a bigger formula so you have to hit more buttons, but that doesn't make it harder. I don't do that on exams because I know I don't want to take up time. So that is what we just did, all written out for you. Okay, so that is empirical formulas, molecular formulas. You will be tested on those in multiple ways. You want to be comfortable doing that. And it's not that hard as long as you remember the steps. What I see people do is either they forget to do the dividing part, they forget to do the multiplication part if they have to. Sometimes they'll get like 0.5 and they'll round it, and then they need to multiply it. Or occasionally I'll see someone who knows they're missing something. They get that 2.5, or they get a number, and they know I can't just round this. And they sit there for half an hour, beating their head against the desk, trying to figure out what they need to do. So as long as you remember the steps, this isn't that hard. It's just a matter of remembering the steps. So we're going to move on to chemical equations. A chemical equation is how we write a chemical reaction. So that's what we started talking about in the video. But before we can talk about specific reactions, we need to learn in general, how do we write that out? In the video, there were some examples of reactions and that possibly you didn't quite understand every little bit of. So the first thing we have to have when we write a chemical equation is a balanced equation. An equation has to be balanced. An unbalanced equation is of no use whatsoever to you. A balanced equation means that you have the same number of atoms of each element and the reactants as you have in the products. In our class, in any sort of general chemistry class, you are not going to create elements, you're not going to create atoms, you're not going to destroy atoms. If you start with 6 oxygens, you better end with 6 oxygens. They may get rearranged so that they're bonded to different things, but you have to end with the same number of each element that you started with. So this is an example of a chemical reaction. Okay, this is how you make liquid iron. Okay, so this is a very energy producing. I want to use a term you haven't learned yet. It's a reaction that gives off a lot of energy. So it gives off a lot of heat, and it ends up making liquid iron. So you can take that liquid iron, pour it into a mold, and make something out of your iron. You're taking solid aluminum, mixing it with iron 3 oxide. We get this going on, we get aluminum oxide and liquid iron. On the left-hand side, these are our reactants. Those are the things that react together to make products. The products are on the right side. This is our yields arrow. Reactants yield products. So the reaction is going to proceed this way. You read it left to right. These things react together to make those things. But it has to be balanced. So let's look at this. If we look at our formulas here, on the left we have 1 aluminum. On the right we have 2 irons and 3 oxygens. Over here we have 2 aluminums, 3 oxygens, and 1 iron. Do we have the same number of each element at the beginning and the end?
No.
No, clearly not. And so this is not a valid equation. We're going to have to alter that equation to make it balanced. Here we're starting with 1 aluminum. We end with 2. So we need to have 2 aluminums over here. Here we're starting with 2 irons. We're ending with 1. So we need to end with 2. In order to balance an equation, we're going to add numbers, and these numbers are going to be called coefficients. A coefficient goes in front of a formula. You cannot change subscripts. Subscripts are set in stone. They're based on the ionic charges. They're based on what the molecule is that you're working with. These cannot be changed willy-nilly to balance an equation. If we want to change something, we have to change a coefficient. Coefficients go in front, and when you put a coefficient, it's going to multiply by everything in that molecule. So if we put a 2 here, we're going to go from 2 ions to 4, and from 3 oxygens to 6. That coefficient applies to everything in that molecule. So, first thing, let's look at our aluminums. We started with 1. We needed 2. We can just put a 2 in front of our aluminum. Because here aluminum is all by itself, we didn't affect anything else. We put that 2 there, we fixed our aluminum, and we didn't affect anything else. Now, our oxygens are okay. They were already okay, but our irons were not. Originally, we had 2 on the left, 1 on the right. So I can just put a 2 right here, and now I have 2 irons on the right, and now everything is balanced. If it is balanced, it's a valid equation. Here's another reaction. This is methane, natural gas burning with oxygen. Methane plus oxygen yields carbon dioxide and water. We need to count, figure out, is this balanced? We have 1 carbon on both sides. Here we have 4 hydrogens, here we have 2, here we have 2 oxygens, there we have 2 there, and 1 there. So is that balanced? No. So we are going to have to balance it. Yes?
So, is that how you get acid rain?
Sort of, yes. There's a step missing now.
Oh.
And so if you put carbon dioxide in water, you're going to make carbonic acid. And so the more carbon dioxide we have in the atmosphere, the more CO2 is going to be dissolved in the rain, and so the more acidic it will be. So we're going to balance this. And sort of like our Lewis structures, I see this as a puzzle. And the more times you do it, the quicker you'll get. You'll find shortcuts, things will jump out at you, and you'll know what you need to do. But you just got to do the work to get to the end. No matter how long it takes you got to keep going. So I'm going to write this down up here so we can balance it. So, some tips and tricks. Do hydrogen absolutely last unless you have a reason to explicitly think I shouldn't leave hydrogen for last? Leave oxygen usually second to last. Halogens like third to last. Metals and carbon and sulfur, phosphorus, things like that probably will be the first thing you do. So in this case, let's start with carbon. Are my carbons balanced?
Yes.
Yes. I have one on each side. So now I've got hydrogens and oxygens. Normally I would say leave hydrogens for the end, but in this case there is something telling me, actually no, we are going to leave hydrogens for the end. I look up here, and what you should notice, and this will save you some time, is over here our oxygens are only in O2. Do you see that just all of the oxygens over here are bound up in O2 molecules? That means they come in pairs, which means we have to have an even number of oxygens on the left. We have 2, 4, 6, 8. We can't have an odd number. Over here we have oxygens that come in pairs, and here we have oxygens that come in singles. If I have an odd coefficient here, I'm going to have an odd number of oxygens on the right. I'm going to have 1, 3, 5, 7 oxygens here, plus an even number is going to give me an odd number. So the very, very first thing that I would do is get an even number of oxygens. If you put a 2 there, I now have an even number of oxygens. Now let's look at our oxygens. Are our oxygens balanced? Now that I wrote that 2.
Yes.
No.
No.
You need 2 on the left side.
I have 2 here. Over here I have 2, O2, and 2. There's 2 waters. Each water has 1 oxygen, so I have 2 oxygens here. So I have 4 over here. I have 2 over here. What can I do? I can put a 2 on my oxygen. Now my oxygen is fixed. Now let's look at our hydrogen. Are my hydrogen balanced?
Yes.
Yes. Now they are. When I fix the oxygens, I actually fix the hydrogens also. Here I have H4. Here I have 2 H2s, which is 4. I didn't add a coefficient to anything that had a carbon, and so my carbon is still okay. I didn't mess up my carbon. Everything is balanced now. So this is our balanced equation. So that's essentially what we went through. Here's some more. These were given words, not formulas, and so you have to figure out the formulas. And you need to make the formulas correct, because if you make the formulas incorrect, you may make an unbalanceable equation. So make sure you get your formulas correct. So first is potassium chlorate. chlorate is not one of those ones you had to memorize. And so I'm going to tell you chlorate is ClO3 with a -1 charge. And so potassium chlorate is KClO3. And that says potassium chlorate yields potassium chloride. What's the formula for potassium chloride?
ClO2 minus.
Simpler than that. What's sodium chloride? NaCl. What's potassium chloride? KCl. KCl plus oxygen. Oxygen is diatomic. You cannot just write oxygen. And so it's O2. Is it balanced? No. Are my potassiums balanced? Yes. Are my chlorines balanced? Yes. That 3 only goes with the oxygen. So we have 1 chlorine there, 1 chlorine there. My oxygens are not. What would be the first thing you would do to start working on your oxygens?
I put a 3 on the oxygen on the right side, on the O2.
Okay.
And put a 2 in
So I need 6 oxygen.
That'll work. Yeah, so
And put
you
a
want to put a
2
3 there,
on the potassium chlorate.
and then a 2 there. Now I have 6 and 6.
Put a 2 on
And then you just put a 2 on the potassium
Right.
chloride.
Because I put a 2 there to fix my oxygens, I ruined my potassium and my chlorines. Now I have 2 of each, but over here they're together, so I can just put 2 like that. That is perfectly fine. My mind always goes to that I have an odd number of oxygens. And so my mind would have put a 2 there and then a 3 there. But we ended up in the same spot, right? Doesn't matter which one you put first, as long as you get them both written. So that is balanced. Now we've got hexane. C6H14 plus oxygen gas, remember it's O2, yields carbon dioxide plus water. It's telling us states. And so if it tells us states, or if we know what those states are, we have to write them. And so hexane is a gas. Well, actually, we don't know what hexane is. It can be either. We're gonna say it's a gas. Oxygen, it says oxygen gas. So I have to put gas. What's carbon dioxide at room temperature? Gas. What's water at room temperature? Liquid. So I put my state symbols in. Is it balanced? No. Are my carbons balanced? No. Let's fix those first. What do I need to do?
6
I put a 6 there. Now my carbons are fixed. Are my oxygens balanced? No. What do you want to do with oxygens? What's the first thing you would do with your oxygen? I would put a 2 on the water. You're going to have an even number of oxygens. So let's get an even number of oxygens and then reevaluate.
So 7 on O2.
So how many oxygens do I have on the right?
14.
14. 6 times 2 is 12. Plus 2 is 14. So I need to put a 7 there. Are my hydrogens balanced?
No.
No. I have 14 on the left. How many do I have on the right? 4. And so, what can I do to get 14 on the right? I can change my 2 to a 7, right? Now I have 14 hydrogens and 14 hydrogens. But what did I just do to my oxygen?
Changed into an odd number.
I changed it to an odd number. I can't have an odd number. And so what do you think I can do?
Double C6.
So, you're jumping ahead. So let's go step by step. You're fine. You're just working ahead. So I need this number to be a multiple of 14, right? Oxygen, hydrogens over here only come in multiples of 14. If I made this 14, then my oxygens were impossible. So I am going to double this to 14. What does that mean I have to do with my hydrogens now, though? I need to put a 2 there. I now have 28 hydrogens here. I need to put a 2 here to get 28 over here. Now, I just messed up my carbons, though.
12.
And now I have 12. So what do I have to do?
Put a 12 in this
I have to change my 6 to a 12. Now we can come back to our oxygen. Now what do I have to do with the oxygen? How many do I have on the right? I have 24 plus 14 is 38. And so what number needs to go there?
19.
19. So now, are we finished, or did we mess something else up on our way? We have 12 carbons. We have 12 carbons. We have 38 oxygens. We have 24 plus 14 is 38. And we have 28 hydrogens and 28 hydrogens. You just have, yeah, go ahead.
Are there any shortcuts for that?
No. You just got to keep going. You just got to keep going. Yeah.
So we're gonna have like few questions like the first test. Because it'll be long to do these, I guess.
The first, what do you mean? Problems like the first?
Not as much questions on the test.
Oh, it'll still be 20 and 3, but there won't be a whole list of these to do. There will be one.
Okay, then.
Yeah. I most likely would not write you a question that required the back and forth like this. But if you do come across a question that I didn't write, and it seems like it's going back and forth, you just got to keep going. You got to keep going until you get it balanced. So let's do number 3. This one should be a whole lot simpler. We've got zinc plus HCl, zinc plus hydrochloric acid forms zinc chloride. What's the formula for zinc chloride? ZnCl2. Zinc has a 2 positive charge, so it's ZnCl2 plus hydrogen gas, H2. Is it balanced to start with?
No.
No. Are my zincs are okay. Let's do the chlorine. So the chlorine's okay? No, what do I need to do?
Put a 2 up on the HCl.
Put a 2 on my HCl. Now my hydrogens are okay. That one's a lot easier.
This is a little off topic, but whenever we're doing these like on homework for the test, do we have to put like what state it's in before, or do you care? Can I guess?
If you see it on an exam, most likely it's going to be in a multiple choice format. And so what it's going to be is it would be this, and then there would be blanks here. The states would already be written in for you, and so the question would say, what is the coefficient on zinc in the properly balanced formula? And so you don't have to do anything with the formulas then. Really, where you're going to come across equations where you have to write those states is in the lab. In the lab, you're going to be dealing with it, so it's obvious what state it's in. And so you need to write that state down. We did. Okay. I want to briefly, we're not going to go too much further. This is what the video went over, okay? And so we're going to pick up on Thursday and do most of this in class on Thursday, but we have a little bit of time, so I just want to go over some of what the video talked about. So we said that there are 4 types of reactions. We had decomposition, synthesis, or combination, same thing, and there's single displacement and double displacement. You need to, 1, be comfortable if you see a reaction, just like our question at the beginning. If you see a reaction, tell me what type it is. And then for single and double displacement, you need to be comfortable predicting the products. If I give you 2 reactants, what are the reactants? There's no way for you to predict products for decomposition and synthesis. That's not something I would ever ask you to do. So if I'm asking you to predict products, that should immediately send the bell off in your head. It must be one of these 2 types. So decomposition was about as simple as it gets. There's 1 reactant. That is your key. If you see a reaction where there is 1 reactant, all it can do is fall apart. That's all it can do. So that is a decomposition reaction. If you see a reaction where there's 1 product, all that could have happened is some things came together to make it. That is a synthesis or a combination reaction. If you see 1 product, it's a synthesis reaction. Here we have 2 elements coming together to form a compound. You can also take an element in a compound to make a compound, or you can take 2 compounds to make a bigger compound. It doesn't matter. If you have multiple things coming together to make one thing, that is a synthesis reaction. We had single displacement. A single displacement, here the key that tells you it's a single displacement reaction is in our reactions. We have an element, and that element is going to be a metal. We have an element in a compound. That compound is going to be aqueous. And then in the end, we also have a metal, an element, and a compound. We started with an element and a compound. We ended with an element and a compound. But there was some switching that went on. So if you see a reaction where you have an element and a compound, and you end up with an element and a compound, there's more than 1 product, so it can't be synthesis. There's more than 1 reactant, so it can't be decomposition. This has to be single displacement. And so in a single displacement reaction, this metal is going to kick out that metal and displace it or replace it. Displacement and replacement get used interchangeably. So in this case, A kicked out C to make AD, and now C is floating around on its own. Yeah.
Did you say it's always going to be solid without these?
It'll always be aqueous. I think in this class it is safe to say it will always be solid. It doesn't have to be solid. So in the actual reaction down at the bottom, zinc kicked out the copper to make zinc chloride, and now copper is floating around by itself. In double displacement, we had 2 compounds. They're both going to be aqueous, and we end up with 2 compounds. The products can be aqueous, they can be solids, they can be gases. That doesn't determine whether it's single or double. Okay? If you have 2 compounds, and you make 2 compounds, that's a double displacement reaction. All we did is we switched partners. The C is now with the F, the E is now with the D. We ended up with silver chloride and potassium nitrate. They switched partners. For the single replacement reactions, we had the activity series. The further you are up on that activity series, the more reactive you are. The stronger you are, the more able you are to push someone else out of that compound. In a single replacement reaction, remember we have an element and a compound. The more reactive element wants to be in the compound. If it starts out that the more reactive element is the single one, the loner one, it's going to kick out the other one. If the stronger one is already in the compound, then the weak one can't push it out and nothing happens. And so we look at here and figure out where our two elements are. So it says if we have aluminum, will it displace hydrogen? Aluminum is there, hydrogen is there. Aluminum is stronger. So aluminum will kick out hydrogen and you will get a reaction. Will iron displace zinc? No. Zinc is stronger. So if zinc is already in the compound, nothing is going to happen. In our double displacement reaction, in order to figure out what the reaction was, we used the solubility table. This and the activity series are both on your cheat sheet. This is not something you have to memorize. So for a double displacement reaction, you switch partners and then figure out, once I switch partners, now what do I have? Are those two things soluble or insoluble? We will pick up here on Thursday. We'll do, and this is an important thing, something you'll do a lot, so I want to do an example of this with you. So we're going to stop here now. We will go over homework before the quiz. Are there questions about what we went over today?